Hello guys, here we are again. Let me see again. Yeah, recording. We are. So, 2 degrees of indeterminacy or multiple degrees of indeterminacy. We're going to use the force method or the consistent deformation methods or the flexibility methods. All of those are basically synonyms in this case. First step, eliminate as many redundants as we need to eliminate in order to make this statically determinate and stable. How many degrees of indeterminacy? How many reactions do we have here? We have AY, AX. I know AX is 0, but nonetheless is a reaction. BY, CY, and DY. So 1, 2, 3, 4, 5. One body. R equals 5. N equals 1. 5 minus 3 times N equals 2. Statically indeterminate of second degree. So we have to eliminate two redundants. Easier, B and C. You can eliminate anything. You can even change. You can eliminate one deflection and one rotation. You can do a bunch of things that you can. You can put a hinge here and separate this in two parts. In that case, you eliminate the moment at this point. Internal moment, I mean, at that point, and then you apply a moment. It doesn't matter. Eliminate two redundants, but in this case, the easiest way to do, eliminate these two. So this is what we're doing. We're gonna have our primary structure A and B, A and D, like that, with the load on top of that. And we know that if this is the primary structure, this is going to deflect like a simple supported beam will deflect, because that's what it is. So this one is our primary structure. Primary structure in most of the textbooks is associated with the subindex 0 or not. So this is what we have. And at B and at C, right there, we have a deformation or a deflection that shouldn't be there. It shouldn't be there because in the original structure it's not there. But that we're gonna fix that out right now. How? With our virtual structure. First virtual structure is this one. What do we do? At the point B, we apply our force of 1 for our virtual work method, and this is gonna produce a deformation like that, and that is gonna allow us to calculate our flexibility coefficient at B when you have a force applied at B. But at the same time, it's going to produce a flexibility coefficient at C when the force is applied at B. This is what happens here. And on top of that, we need the second virtual. And the second virtual, then we're going to push this to 0. Or try to, at least. So when we do that, we're going to have a deformation like this, like that. And that basically is telling us that at this point, this is going to be the flexibility coefficient at the point C, where the virtual load is applied at C, and this is the the flexibility coefficient at B when the load is applied at C. Now, once we have this, we can go and we can work the problem out. As a matter of fact, let's start working it here. So I know that this is 2 kip per foot, and I know this is 20, 40, 60. So if I want to know the reactions, this reaction and this reaction, it's easier to calculate this here instead of killing more trees in the other papers. So this is going to be a reaction like that, dy, for this one, and it's going to be, once again, 2 times 60 divided by 2. That means that it's going to be 60 kip, and as well as this ay here, which is 60 kip. Good. And now I have to calculate the reactions here and the reaction here. So I'm going to have a reaction here and a reaction here. If I apply the load going up like that, my reactions are going to be in the other direction, something like that. If you do you can say this is something that you you should learn already, because this load is closest to this part. Then it's going to be this distance divided by the total. This distance is 40 divided by 60. 40 divided by 60 is 2/3. So this reaction here is going to be 2/3, and this reaction here is going to be 1/3. But it doesn't matter. I mean, you don't have to do that. You can do summation of moments here, and then you say 20 times 1 divided by 60. That's 20 divided by 60, 1/3. And then summation of forces in y, and then do the other one. Same thing with this situation. In this situation, we're going to have this one, this, and this. I don't know if you have noticed it already, but these two are symmetric because all the distances are symmetric. So basically, this reaction here should be 2/3, and this reaction here should be 1/3. It's the mirror image of this one here. Basically the same thing. So now we have the reactions. What is the next step? The next step is calculating every one of these coefficients. Now, instead of me going through the virtual work and repeating and making a 3-hour long video, because that's basically what it will be, a 3 hours long video, I'm going to use a formula for that. So we have this formula. This formula here. In the back of your books, you have this formula. I'm going to copy the formula here again. For a simple supported beam, for this simple supported beam, depending on what I need, using this formula, depending what is the distance x that I need to calculate the deflection, and this is L, the distance L, then I can calculate my deflections using this equation, and the deflection, they call it V, is equal to 24 what is that, Wx divided by 24 EI multiplied by x to the third minus 2L x squared plus L to the third. That's basically the equation. Meaning, what do I need to calculate? I need to calculate delta B0, and I need to calculate delta C0. These two. At delta B0, x will be 20, and of course L is 60 for that. So then I just have to plug this into that equation, and I get negative, because it's coming downwards, negative 20. I don't like to put the sign here. I like to study the sign instead of giving the equation. The equation actually has a negative sign here, but I like to say, oh, this is a negative deflection because it's going downwards, and I take control of that. And W, of course, is equal to 2. So this is going to be negative 293.3 divided by EI, because in this case EI is constant. I didn't say that, but EI, assume EI is constant. Now, that will take care of this delta V0. Now I can calculate delta C0, and I could do that, and then I can put x equal to 40 and 60, but as I said before, this is delta B0, but because this is symmetric, it's the same case if I'm measuring from this end to here, x to 20, and that will give me the value at this point. So delta B0 is equal to delta C0. I don't have to calculate it twice. But if you want to, don't take my word for it. Calculate delta C0 as W using x equals, you can use also x equals 40 if you want to. X equals 40 and L equals 60. And then you will get that deflection here, delta C0. But it's going to be equal to this one per symmetry. Now the next step is calculating FBB and FCB. So for FBB and FCB, what we have is a different equation now. We have this equation here. And this equation for deflection is, and I know my students are starting to think, Professor, are you gonna let me use this in my exam? I'll think about it. I'll think about it. So what we have is this, and the force P is here, and then you want to calculate the deflection at any distance x, and then this is x, and then this distance up to the application of the force is A, and this distance is B, and the total distance is L. This is basically the drawing that you have in the backs of the books. There are different books, there are different formulas, but they are all very similar. So the formula is, they put negative also because the load is going down. In our case, it's going to be positive because it's going up, but that's why I like to put just this. PBX, P times B times X divided by 6LEI, and then you have L squared minus B squared minus X squared. By the way, in the FE and PE, if you have to calculate anything like this, you're going to have the formulas. You're not going to have to do virtual work. And this works from 0 smaller or equal than X smaller or equal than A. So basically this is wrong. This is not X here. X should be here. And if I want to use it the other side, then I have to switch it. Anyway, so we have that. Now, if we have that situation, and I have to calculate this FBB right there, FBB, then for FBB, the deflection at that point, let's check what are our values. For FBB, you have A up to that point is 20. A is 20. B is 40, because B is this distance, is 40. And X is the value where I want to calculate the deflection, which is exactly at the point, so X, it will be also 20. And of course, the value of the force is 1, and L is 60. So once I put this into the equation, I come with FBB equals 3555.5 divided by EI. I have that one. Now, surprise, surprise. This FBB, remember when we are going to do that, because this is symmetric, FBB is going to be the same FCC. This one here. It's going to be exactly the same deformation. And that's simplifying our problem a lot. Now, the other one that I have to calculate is FCB. This one here, FCB. Well, for FCB, what I'm going to do is I'm just going to use the same formula, but I'm going to measure it from this end here. So I'm going to say my A is here. This is my force of 1, right? And I'm going to say this, my X from here is 20, because I want to calculate it at this point, and this distance is 20. This distance from here to here is going to be A equals 40. This distance is going to be B. I'm just flipping this thing, B, because of this condition. There are books that these conditions don't apply, but you have more conditions to check. And I want to calculate then the deformation at that point. That's what I have to do. So if I do that with these values, and of course P equal 1 and L 60, but I switch my values around like that, then what you are getting is that FCB, when you put these values into that equation, then you get FCB equals 3111.1 divided by EI. And once again, guess what? That FCB, which is this one, per symmetry, is the same FBC. You see how practical these formulas are? And we are almost done, believe it or not. We're almost done. No, we are done with this part. Now, what do we have to do? We have to apply the principle of consistent deformations. Where is my front page? Where is my front page? Nobody moves. My front page got lost again in this nightmare of desk that I have. Front page. There you go. Okay. Now, if you look at this one, what you have to do is this. The deformation here is 0. Here, deflection here at this point should be 0. So 0 has to be equal to the summation of delta B in my original, which is going to be negative because it's acting downward. And then I'm going to push it up here and here. The flexibility coefficient for this one is going to be FBB times, that was for 1, but what I'm looking for is BY. So times BY. And when I push it here with 1, it's producing FBC. FBC. But I'm not going to push it with 1. I'm going to push it with CY. And in the other point, here, the deformation should be 0 also here. And that means that this is delta C in my original or primary, plus, now, when I push it here, that is producing this deformation here, which is FCB multiplied by, if it was 1, but now it's not 1, it's BY. So BY plus, now push it here, it's going to be FCC times CY. And now we have a system of two equations with two unknowns that we perfectly can work. Now let's plug in the values that we got before. What are those values? Well, delta B0, which is this one, I'm going to put it there, is negative 293.333.3 plus FBB, this one, 35,3555.5 times divided by EI. Everything is divided by EI. Okay, so if everything is divided by EI, that's going to be passed to the other term and it's going to cancel out. So I don't care about that. So times BY plus FBC, and FBC is this one, 3111.1 CY. Now in this case, delta CO, which is the deformation here, delta CO, we calculate it and we say it's the same value, so negative 293.333.3 plus FCB. FCB is this one, 3111.1 BY plus FCC, and FCC is this one, 3555.5 CY. Solve this system. How do you solve that system? I don't know. Whatever you feel like solving the system. You can multiply, you can divide. If you want to eliminate this one here, you just multiply this by negative 3111 divided by 3555 everywhere. And you can use your calculator, you can solve it, but at the end, you're going to get that BY is 44. Keep. And CY is also 44 keep. And those are our redundants. So if these are my two redundants, now I can go to the original equation here and calculate the real AY. But the real AY then is going to be, if this is 44 and this is 44 and this is 120, 120 minus 88 is 32. 32 divided by 2 is 16. So AY is going to be 16 and DY is going to be also 16. And we finish our reactions. Now what is the next step? The next step is draw the shear moment diagrams. Well, the shear moment diagrams for this, let's use another piece of paper. I'm sorry, trees. I'm gonna call another tree. I'm gonna kill another tree, not call another tree. I'm gonna call a tree. Hey tree, come here, tree, I'm calling you. So this is what I have. This is 2 kip per foot. Right there. This is 16. This is 16. And then you have here 44 and 44 in kips, of course. And all the distances are 20. 20. Line, 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 line. Those are called discontinuities or points of interest. V, M. Oh, this is the first time that you are seeing a continuous beam shear diagram, and you should get familiar with that because it's a fairly common case in real life. But it's the same procedure. I go up 16, so this is 16, and then I'm gonna come here and I'm going to find 2 times 20, 40, 40 minus 16, it's gonna be 24, 24, straight line, or it's supposed to be a straight line. Now find 44, pushing it up, and you get 20 right there, and then you have 20 times 2, 40, 20, that should be 20 here also. I don't know why I don't use a ruler instead of being flipping this, but anyway, negative 20, and then now this is going to be pushed up. This is 20, this is 44, meaning this is going to go to 24 somewhere here. Look at that, 24 and 20, but it doesn't matter. This is not the scale and you know it, and I know you know it. So 24 right there, that point should be here. Now it's going to be bothering me for the rest of the lecture. 24, and then you have 2 times 20 is 40, 40, 24, negative 16, negative 16, and this goes from here to here, and then you find this 16, 0, yes. Now the moment the diagram is going to be like that, if this is 16 and this is 24, 16 plus 24 is 40, it's 40, and 40, that means that this value here should be 8 and this value here should be 12, right? Let me check it. Let me check it. 16 times 2. Yep. You say 16 plus 24, that's 40. So you say 16 divided by the summation of both, 40 divided by the total length, 20, and multiply by the total length gives you this value. And if this is 20, this is 8, and this is 12, in this case everything is symmetric, so this is going to be 10 and 10, and in this case this is going to be inverted, so this is going to be 12 and this is going to be 8, like that. And now we just do positive, negative, positive, negative, positive, negative, and then we just do please don't neglect infants, neglect dumb people instead. And this is positive decreasing. Positive decreasing means it's going to be this. The area of this, 16 times 8 divided by 2 is 64. So this is going to go up to that point like that, which should coincide with this. And now this value here is 24 times 12 divided by 2. 24 times 12 divided by 2 is 120. This value here is 64. I say 64. No, this is 24 and this is 64, right? Yeah. So 64, and this is 24 times 12 divided by 2, 24 times 6, 144 minus 64 is 80. So it's going to come here to negative 80. Negative increasing, negative increasing, negative increasing, negative increasing, like that. And now you go here, you're going to have another maximum minimum. Here you're going to have another maximum minimum. This is 80, this is 200. 200 divided by 2 is 100 minus 80, 20 positive, positive decreasing, positive decreasing, positive decreasing. Now we are going to have here 100, so this is 20 once again. I put 20 over there. This is negative 20, and this value here is 20 the moment. Now this is 20, this is negative 100, is going to come down to negative 80 again. And now this is going to repeat because this is everything is symmetric. But if you want to use the formulas, you use them. 64, 0, yes. And now what do you do with this thing? Well, when you go on your study, for example, reinforced concrete, you can see that at the supports you have a negative moment, and at the center of the spans or at the spans you have a positive moment. If you have reinforced concrete and you have a beam in reinforced concrete, for example, you know that if this is the support reactions here, what we have, and this is the reinforced concrete beam, whenever you are in between these two, the majority, I'm not saying that this is going to be cut like that, the steel is going to be continuous, but here, here, and here at the bottom, you're going to require more steel because this is the parent tension. That's why you have the steel at the bottom. Now, in the supports, then you can see that the moment is negative. The moment is like that, so the tension is going to be in the top. That's why when you have a negative moment, then you have to reinforce this part here on the top. But this is, I mean, just extremely simplified analysis. I hope that you like this video, and if you didn't like the video, it's so easy. Don't watch it. Okay, don't watch it again. Bye guys, see you later. Stop.